seen the PCA helpful handout. So basically, I've given you the entire code, okay? And the reason is, I know some of you made some progress, but we're not getting correct results. Our next several assignments depend on this part, okay? So I would like you to, make this in working order, and also, understand it nicely so that you can do the next part nicely, okay? So I'll briefly go over the code so that it's always difficult to understand somebody else's code. So let me at least go over and explain how it's organized so that it makes sense and you can enhance it for the next part, okay? Okay, so remember our data set, if you recall, is AT&T data set. It has 40 persons.
10 images of each.
And 10 per person, right? So typically what we do is use half the data for training and half for testing to see how well it's working. So basically, if you take a look at the two folders I gave you, one was called training and one was called testing. So basically, it has 40 times 5 images of one person and 40 times 5. So half the images will create the PCA bases, project all the images on these bases so that every image can be represented by this variable over here, number of eigentraces. So if we pick this to be 5, that means there are 5 basis vectors, or the number of dimensions that we are reducing our data to is 5. If we make it 20, 30, 40, 100. So one of the things that I like to understand nicely, because this, like I said, relates to some of the deep learning concepts that we are going to cover very, very soon. So for example, these 40 people, each image over here is 92 times 112, right? So that's the size of each person's face. So if you recall, once again, the algorithm goes assemble it all the pixels into a vector. So we convert it to grayscale and assemble it into a vector, right? Okay, now each image over here, the 10 is recognized as like S25 underscore 1, S25 underscore 2, S25 underscore 10 as an example. So if it's person number 25, it has 10 pictures of it. That's how they are organized. So one of the things we want to do is, as we read each image and store it in a vector, we also want to know what is the name of this image so that later on, once we recognize, right? So for example, as we are testing, suppose we feed in, so over here, these will be S25 as an example, 1 through 5, right? Here, suppose we feed in S25, 7. So after the PCA is done, right, it will tell us what is the closest match. Suppose it says S25, 4 is the closest match to S25, 7. So then how do we know it's the same person or not? Just by looking at the ID of the image. As you can see, all we have to do is take a look at the first 3 characters. And if they're the same, it's the same person. If they're not, so this is how we can easily determine the accuracy, right? So, okay, so as a high-level idea, the way the code is written is, let me go to Notepad. Closed it. Okay, so I created a class called myImage. Okay, inside it, it has an image vector. array. Okay, and as you can guess, this will basically be all the pixel values. So this will be 92 times 112 and all the grayscale. So we read, so in this class we'll also have like a short name. So for example, this could be S25-3 as an example, right? Okay. So once we have assembled, or once we have read the entire training data and stored it into one object of my image class, okay, so then basically we can create a list of my image as an example and store all the 200 images in it. So each one has image vector with all the data. Okay, so as you can see, first thing we need to do is subtract the mean from each image and assemble it into an I matrix. So I will be, what I basically did is as I subtract the mean, I stored it into another array, image vector, I forgot I called it adjust m. So basically this minus the mean image is saved over here. Okay. Then if we assemble all of these, 200 of these into an I matrix. So as you can see, the dimension of this will be 92 times 112 times 200, right? Because there are 200 training images. This is image 0, image 199. So then what do we have to do? Compute the covariance matrix. Then what do we have to do? So the covariance will be I transpose times I, correct? So this will come out to be 200 by 200. Okay, then what do we have to do? Compute the eigenvalues, eigenvectors. Okay, so what I do is I create an I matrix using the MOPAC library. We can multiply the two matrices. Using MOPAC library, as I showed you the 3-line code, we can compute the eigenvalues, eigenvectors. Okay, now if it was Python, we can sort on a particular axis, but in C#, and that's one reason Python is more popular for machine learning and deep learning, is because it has much better matrix operations. Okay, so here, maybe there's a better way to do it. So what I did is, so basically what this will do is it will give me, once I use the MOPAC library, it will give me an array of eigenvalues. And corresponding to each one of these, it will give me an array of eigenvectors. Okay, so can you guys tell me what will be the size of the array of the eigenvalues? Remember on this covariance, which is 200 by 200, we're computing the eigenvalues. So this will be 200 by 1. And each one of these will be 200 by 1. And how many there will be? Corresponding to each eigenvalue, we have an eigenvector, right? 200 of these. Okay. So, but now the question is, remember, let's say we sort these. Let's pretend the third value is the highest eigenvalue. So what does that mean? Correspondingly, the third index should be maintained, the other should be tossed out. Right? So what I ended up doing is, so like I said, that there might be a better way to do it, but basically what I did is I created another class. I called it EVEVEC, short for eigenvalue, eigenvector. Okay. So then inside it, each object So each object has one eigenvalue and one eigenvector. So I basically created a list of these. Okay, so I picked one of the eigenvalues, put it in one object, corresponding eigenvector, I stored it in the, right, and then added it to the list. Okay, the advantage is, after I have assembled each one of these into a separate list, then C# gives us a sorting capability on the list.
Yeah.
If we implement comparable interface and tell it the field to sort on, so we'll sort all the objects in the list. So which field will we pick to sort on? Eigenvalue, exactly. So then we can, if we wanted to pick, let's say, number of eigenfaces to be 20, then what we can do is keep the 20 objects, throw away the rest. Okay. So then we can take those 20 objects. For example, if we, right, we can assemble them into another matrix. Okay, so what will be the size of that matrix if I just pick 20 of these eigenvectors? What's the size of each eigenvector? 200 by 1. If I take 20
of them, so 200 by 20.
200 by 20. Right? Now if I took my I matrix, which was already assembly of the mean adjusted images, right? So the size of this was 92 times 118, or sorry, 112 by 200, because we had 200 images in the training, right? So if I did as if I did, for example, transpose of this, right? No, sorry, transpose of this and multiplied it by this. I'll get 200 by, or let me do this. Let me just take this, sorry, take this and just multiply it by this. So then won't I get so each one of these will be 92 times 112, and how many of these will be? 20 of this. So this is what we call an eigenface. If we scale each number between 0 to 255 and display it, it will look like a ghost face, right? Then any incoming image can be projected on to our eigenfaces, so that, so for example, now each image, remember, is 92 times 112, right? Mean adjusted, of course. Okay, so suppose this is Ix. So what do I have to do to these two to get the 20 number projection? This is basically 92 times 112 times 20. So as you can see, if I did, so this is times 1. So if I did a transpose of this, multiplied it by this, won't I get 1 by 20? And that's the projection of this image onto this space. And we call that the face space as an example. Okay, anyway, so the code is essentially doing exactly what I described to you. So if you see the eigenvalue, eigenvector class, again, if I was doing it in Python, I won't need this because I can easily sort on a given axis. But here, I assembled it into a list so that I can sort it and throw away those eigenvectors. So there was a little bit of a transformation going back and forth over here, some additional overhead, but hopefully if you now take a look at the code, it should make perfect sense.
So your list has 20 objects.
In the beginning, list has 200 objects.
200. Yeah, but then when you get the...
We sort it,
Yes. and
then we keep the top 20 out of this list. Okay, so now if I show you the code. Okay, so let me first go to my image class. Okay, so my purpose of my image class was, like I said, two main purposes. It has to have a short name for the image. For example, S19_5, right? Also, all the data should be, and I called it, like I said, image vector. All the pixels after converting to grayscale, right? I stored additional things later so that I could use them later on, but for the purposes of this assignment, really the image vector and image vector adjust mean is subtract the mean, and that's the data that's important in this class. Okay, so ID is, for example, the file name short is what we go by, like S19_5, right? And very briefly, and I try to comment it as much, so these are all the pixel values. This is
Adjusted.
minus, oops, it should not say brightness. I was doing some additional things over here. It's really for the code you have is just doing minus the mean image.
Ours doesn't say that, that's good.
Okay, so yeah, I might have corrected it. Okay, then this is the projection. So this is basically, if we use 20 eigenfaces, this will be 1 by 20. If you use 50 eigenfaces, this will be 1 by 50 as an example. So this is basically the projection onto the reduced dimension of this particular image. Okay, and few other fields are there. For example, there's a correlation error, Euclidean error, that basically tells us the distance between whatever the best match we had to this particular image, and so on. Okay, so very, very briefly, let me just quickly show you EVEBEC, which was totally for the purposes of sorting the eigenvalues. So I made this implement comparable in C# if you wanted to sort any object of a class in a list. This is where we tell it what field to sort on, right? So as you can see, the data over here, as we discussed, is a single eigenvalue and the corresponding eigenvector that we've already obtained from the covariance matrix, right? Okay, so then this I comparable has one simple function called compare to. So this compare to is part of the I comparable interface. And if you take a look, what is it sorting on? The two eigenvalues. So, and the order we put it in, it will do highest to lowest sorting. So the top object in the list will be the corresponding to the highest eigenvalue, then the next and so on. Okay. Anyway, so that was the key over here. Okay, the main class that assembles everything over here is face recognition by EF. So that's what assembles the whole algorithm. So let me briefly show you the key things over here. So in this one, of course, we need a covariance matrix. We need the matrix, which is the assembly of all the mean adjusted images, right? And a few other things over here, but anyway, let's go to, this is the main algorithm. Okay, compute eigenfaces. Okay, so it prepares a blank image list, a blank eigenvalue eigenvector list. So the first part of the code, as you can see, all it's doing is going to the training directory. Okay, remember where we have 200 images? Picks out each file. Okay, and then reads all the pixels, converts to grayscale, creates one object of the my image, and starts to store in it, and the short name and so on. So this part of the code is simply reading each JPEG file for the face. Right, so this for each over here. Okay, so once we are done with this loop, all images have been read into a list of my image. So at this point, all images are inside a list of my image. So let me see if you guys can guess. Can you guess what will this do?
It says subtract.
Yeah. So basically, right, we add up all the images, divide by 200, that becomes the mean, and then subtract from here, and compute and then we can further assemble it into the I matrix, then covariance. So let me quickly take you to adjust all images code. But anyway, before I go there, so these are the steps of the algorithm. Okay. So prior to this, remember the code was doing read images into image list. Right? Then subtract the mean, because we have to know all the images before we know the mean, right? Then compute the covariance, compute eigenvalues, eigenvectors. Okay, then we basically over here will sort and then compute our bases and then project each image on the basis. Okay. And all of these are small functions you can easily see. For example, let me show you. Like compute covariance matrix. If I go to definition. So how big of a code is it? One liner, right? As we discussed, I transpose times I. And this is the matrix class from the MOPAC library. I gave you a link to it. You can download it, add it to the project. Okay. So that too. Okay, adjust all images, like I said. Let me quickly show you, go to definition. Okay, and I commented it so that it's easier to see, find the mean image, then store it in the AVG image, subtract average image from each image. So I wrote a small function for that, right? Copy mean into the I matrix. So that after we are done, our I matrix will be 92 times 118, whatever that number is, times 200, because we have 200 images, right? So anyway, so this you guys saw was one-liner code. This one, like I said, so let's go over here. First, it will use the same MOPAC library to find the eigenvalues, eigenvectors. Go to definition. Oops, okay. Go to definition. Okay. So anyway, 3-line code to compute the eigenvalues, eigenvectors, like I showed you last time through the library. Okay. Then I further assemble these into that EV and make a list of EVC so that I can sort it easily, right? Okay, and lastly, so anyway, hopefully you guys can go through the rest of it. Let me quickly run it to show you what kind of results, what does it look like. So the first button will allow you to go through the 200 images, read them, assemble it into a list of my images, compute the covariance and the projection of each image so that every image is represented by the that FSV array, phase space vector, which is basically 1 by the number of eigenfaces. If you pick 5, it will be a 1 by 5. If you pick 100, it will be 100. So let's do this first. Okay, if I take you to the form, view code. So in the beginning, this is where you can easily change. So suppose we wanted to run it with 5 eigenfaces only. That means every image will be reduced to 5 dimensions, 5 numbers. So if we run it,
We could open the bottom for the past run.
close that, run it one more time. Otherwise, I don't know which copy is which. Okay, so now if I compute this, it will take 5-10 seconds to read all the images. Okay, so this is what the average image looks like. This is the first eigenface. But here's the neat thing. Any image can be reconstructed by a linear combination of these. You know, as we discussed, if we multiply this by some number that we can determine through the projection times this, so we'll get that, right? So now let me pick an image to show you how the reconstruction looks like. So if I pick this, it doesn't matter, any one of these. Okay, so you will see it's not a very good reconstruction, right? Is it able to recognize it correctly?
I don't think so.
No, I don't think that's the right one.
Because it's 5. We only have
I should have printed the file name there as well, but I think it's a wrong answer. So let's do the accuracy. So if I click on this button, it goes through all the 200 and compares the first 3 labels so that we know what percentage the overall accuracy is. So it takes about, so you can see the accuracy 49%, which is not very high,
But it's
right?
5 faces.
That's 5. Now let's increase the number of eigenfaces, so the dimensionality of the reduction is higher than 5. Let me make it 30 as an example. Okay, you guys will play more with more numbers and give me a graph. So if I make it 30. So again, first you click here. Once it's prepared all the data, then you can pick any image. So if I pick a test image, okay, so it doesn't matter. So you can see it is looking a little closer now, okay, to this one. So this is the reconstructed. I'm only showing you 5, but it's reconstruction based on 30 of these. Okay. Did it find the right one?
Is it the same person just without
I think it's
glasses?
the same one.
Seriously, this is...
Yeah. See, as I will show you later on, I mean, it's amazing how deep learning can even do better than humans. So we sometimes think, no, it's not, but it will do sometimes a better job than us. So anyway, so what's the accuracy with 30 eigenfaces if I click over here? Okay, so it should be done almost. So 89.5%, right? So 30 is not too bad. What if we make it 100? so again, first let me compute all the bases, the 100 eigenfaces as bases. Then if I click over here. Okay, so now you'll see it will be a tiny bit better.
Did you test it?
Yeah, I clicked on computer. Oh, I didn't do that, but I can do that afterwards too. So you can see accuracy is 90%, and the reconstruction hopefully will even be better now. So any one of these. Okay, so that still is making a mistake, I think, on this one. Anyway, this must be one of those 10% cases where it fails. Okay. But reconstruction is starting to look like that person, right? Okay, so anyway, so like the first goal for you guys is, if you already have your own code, but it's not giving same results, try to see where you might have made a mistake. But if, like I said, time is short, we want to move on to the next part and next part. So even if you read the code and understand it, I'm okay with it, so that you're able to at least come to this part, right?
Yeah.
Okay, so the next part is, and I already put that in the next assignment, where you have to convert it, you have to modify this code so that instead of PCA, it does an LDA. So LDA is also a projection, as we had discussed in the previous lecture. Okay, so if you remember in here, in a PCA, how many bases do we create for the reduced dimensionality? Okay, remember we control it, right? We do 5, we do 30, we do 50 or 100, whatever we feel like it, right? In LDA, remember the goal is to provide maximum distinction between the classes. Okay, so the projection is basically number of classes minus 1, as we had discussed in the previous lecture. So how many classes do we have in our data set?
200?
No, not 200. How many classes do we have in our AT&T data set?
Oh,
5%, right?
Is it each person has 10 different?
See, class means category, right? When we distinguish, we want to say you belong, you are this or you are that.
5%, 5%.
So,
How many people?
how many people are there in the AT&T data set?
40.
40. So it's a 40 class problem. So what does that mean? Once we apply the LDA, the matrix it will create so that I transpose times basis matrix. Okay, can you tell me what will be the, see I will be 1 times whatever that 92 times 112 number is, correct? This is the size of I transpose. So in LDA, or let me first go to PCA. If you had 30, you wanted to reduce it to 30 dimensions, what will be the basis matrix? Each one will be